In this subsection, we shall practically apply logistic regression. Recall the exam dataset we had seen previously. We have exam 1, exam 2, exam 3, and then the final mark. What happens here is when a student has a mark of say 73 on 100, 80 on 100, and 75 on 100 on exam 3, we're able to predict a final mark. But this is a linear regression problem since our values span a given range. Now, to convert this into a logistic regression problem, we simply modify the outputs such that all marks below 160 are considered to be field marks. That is, we have 0, like in this case 152, we have 0. Here this mark is above 160, so we have 1, so on and so forth. So we convert this problem into a logistic regression problem which predicts whether from the student's exam 1 mark, exam 2 mark, and exam 3 mark, the student is going to pass the final exam or not. Again, we start with our imports, and then we have this prepare dataset function. It's going to be a modification of the previous function we were working with. So in this case, we have a logistic regression model. Logistic regression model. Now we read the CSV file. Obviously, when calling, we're going to have exam.csv instead of health.csv. We read the file. We have 3 lists x1, x2, x3, and then xy. So x is the input and y the output. X1 is going to take exam 1, x2, exam 2, and x3 the final mark. We're going to leave out exam 3 since we want to be able to demonstrate logistic regression easily using plots. So as assignment, you could include x. Let's say you could take x3 to be the exam 3 and then send this to exam 4 and work with it that way. So let's take this off, and for now we're working with x1 and x2. So we're using x1 and x2 to predict x3, or better still, we're using exam 1 and exam 2 to predict the final mark. Then we have to make up x. We have 1, the bias, we have x1, we have x2. Now for the output, we have that if this is greater than 160, we have 1, else we have 0. Then we convert this to numpy arrays and we return our arrays. So here we have exam.csv, and then we get our x. Let's print this out. So run this, print x. And this is exactly what we have. And then we'll go print out y. Let's just do this, and there we go. So we have x and y. Recall from theory that we work with a sigmoid function when dealing with logistic regression algorithm. So here we've just defined this function which takes in x and then returns the sigmoid of x, which is 1 divided by 1 plus e to the power of negative x, which is this function. Now the gradient descent algorithm here is very similar to what we did for the linear regression problem. We have this random seed, the number of epochs set to say 10 for now. So we have 10 epochs. The learning rate 0.1. The batch size in this case is 25, since this is going to give us 25 from this obviously. So we could print this out here. We have x.shape 0, and there we go. We have a batch size of 25, and then we initialize theta, which is our weights and biases. So we have this theta which gets the shape, and obviously the shape is 3 in this case. We could print this out too. We have 3, so we have our theta, then the loss, and now we're gonna start with a gradient descent algorithm. So here we have this loop. We loop through all the total number of epochs. We have the epoch loss initialized to 0. Then we have this. We saw this already on the linear regression. And the difference now here is for this model output, instead of having just this, that is without the sigmoid, that's instead of having just x times theta, we have now sigmoid of x times theta. And then for the partial derivative of the loss with respect to the parameters theta is still maintained as we saw in theory. Now we have this gradient descent step, which is theta equals theta minus the learning rate times d theta. And then we have the epoch loss. Now note that unlike the previous example or the previous algorithm where we had the mean square error loss, here we have the binary cross entropy loss, which is defined a bit more differently. So in this case we have negative of y, so this is the formula we had, y log y predicted, so in this case we have y predicted plus 1 minus y times log 1 minus y pred. So basically that's what we have done here. So this is our model output y pred, this is y pred, and then this is y target. So there we go. And with this we have this list which basically collects all the losses as we go through the different epochs so that we could plot this after. So let's run this, and we still have this problem of divergence. Now this is occurring as we've seen already in theory because this learning rate steps are too large. But then we saw last time that generally when we normalize this, we may be allowed to use larger learning rate as compared to when this is not normalized. So we could normalize this to a value which is always going to lie between 0 and 1 by dividing through by 100, since all the max range between 0 and 100. So here we have this. Then we run this again. We now find that that normalization has actually helped a great deal. And from this, we could increase the number of epochs so that we could get the best possible values for theta. So we run this again, and then we have this. We find that the loss is actually reducing. We could increase this number of epochs. Our loss now gets to 0.167. There again, we could do this. Our loss drops to 0.1396. And we'll find that our model has actually converged because increasing further doesn't actually help in reducing this loss. So at this point, we could take these values for theta as the best possible values. So this is our theta, which best represents our data set. Now let's go ahead and plot our data set and later see how well our model is performing. We have, as usual, this. We read this data. Now we have x1 and x2. That's big x1 and big x2. And then we're going to put our values for y into categories such that whenever we have y equals 0, that's whenever the output is 0, we're going to plot it as red, and whenever the output is 1, we'll plot it as green. We have the scatter plot, we have the size of 20, then we'll show our plot. So let's run that. So this clearly shows us our plot. Now we are seeing that as the MAC, the exam MAC increases and the exam 1 MAC increases, we have this tendency of having a good final MAC or a pass in our final MAC. Let's see how to include our model in this. So we see how our model will behave when given points which are actually in this domain. That is points ranging from say 40 to 100 and 40 to 100 this way. So we have max, exam 1 max between 40 and 100, exam 2 max between 40 and 100. All these points are going to be tested with our model, and our model is going to tell us how it's going to behave if these points were given as inputs. So here we have for I in range 40 to 100 and for J in range 40 to 100, we have x1, which takes in I, and x2 takes in j. So we're considering that we're having this I, for example, to be the exam 2 max, and then the j exam 1 max, and then we kind of put this into our model and then get some results. Our model output is gotten by using this input. We have 1 I j. We simply normalize this way. So we have 1 ij times theta to give us our model output, and we have a sigmoid function. Now in this case we have a sigmoid probar function. Let's define the sigmoid probar function. This function is defined such that if the sigmoid of our output is greater than 0.5, we return 1, and if that's not the case, we return 0. So we could include it greater than or equals to 0.5, and we run that. So we've defined the sigmoid probar function, which uses the sigmoid function. So that is done basically because the plot functions, we need a 0 or a 1 to either output red or output a green. And so since our model outputs values between 0 and 1, we need to say for all values greater than 0.5 send to 1, and for all values less than 0.5 we send to 0. So that's why we use the sigmoid probar function. Now we have y, which takes in the model output. We have the categories as usual, and then we plot. So let's run this, but this time around with 1, so that it's not as big as this other plots. Here we had size 20, now we have size 1. So let's run this, and we have this beautiful plot, which shows us how our model manages to understand this data set. So we'll find clearly here that when the exam 2 mark is say 100 with an exam 1 mark of even 40, you'll be classified as someone who's going to pass the final exam. Although logically this normally may not be true, but then our model doesn't do this prediction based on something it hasn't seen. So we have to understand that machine learning basically feeds on data sets, or it feeds on data. So it is trying to practically mimic the data set it's been fed with. So we can't actually blame the model for doing this. Now, if we have this kind of problem in real life, all we could do to have something better than this is by getting more data, so that we will be able to better understand the patterns, or the model is going to be able to gain more insight in understanding how to use exam marks to predict final marks. Nonetheless, for the data points we have here, it does quite well because we only miss out twice. So we would have an accuracy of say 23 on the 25 different data points, which is about 92% accuracy, which is not bad, although this could be ameliorated by getting much more data. For the assignment, you're going to develop a model which mimics the behavior of an AND gate. How does an AND gate function? When it takes in one of its inputs 0 and the other 0, it outputs a 0. And here it's going to output a 0, here outputs a 0, and here outputs a 1. So it only outputs 1 whenever the two inputs are 1. So we could use the logistic regression algorithm to mimic this behavior.